Assalamualaikum and hi. My name is Amirul Irfan Haziq bin Muhammad Suhaimi.
Hi, my name is Idrina Alia binti Azra Faiza.
Hi, my name is Nur Faika Dayana binti Muhammad Budiamin.
Hi guys, my name is Wong Wei Xiang.
Hi, my name is Muhammad Faris bin Shamsul Izwan.
Now I will explain about the process flow diagram. The process begins with the mixing of water and isopropyl alcohol in the mixer. This ensures that the feed is well blended before it enters the next stage. Once mixed, the feed is passed through the vaporizer where it is heated to convert the liquid mixture into a vapor paste. Then, the reaction will occur in the reactor. After vaporization, the heated feed enters the reactor, where the dehydrogenation of isopropyl alcohol takes place. In this chemical reaction, isopropyl alcohol is converted into acetone and hydrogen gas in the presence of a catalyst. Then, the condensation and separation will take place. Once the reaction is complete, the reactor's output contains a mixture of acetone, hydrogen, and reacted isopropyl alcohol and water vapor. This mixture is then sent to a condenser, where it is cooled to facilitate the separation of gases and liquids. The cooled stream then enters a separator, which divides the mixture into two parts, which is the top product and the bottom product. The top product contains of hydrogen gas, while the bottom product is remain liquid, which still contains acetone and water. Then it will be sent to the next stage for further purification. The liquid stream from the separator is then fed into a distillation column. This step is essential for purifying the acetone by separating it from water and other impurities. Acetone having a lower boiling point than water. Then it will be separated as a product and collected from the top of the distillation column. Meanwhile, any remaining water and unreacted materials are removed from the bottom, will be recycled back into the process to improve the efficiency. Finally, the purified acetone is stored in the storage unit. Principle of chemical engineering play a key role in making production efficient, cost-effective, and safe. In principle of chemical engineering, there are three main aspects that need to be considered, which is the mass balance, energy balance, and material balance. Mass balance helps us to track the materials to prevent waste. Besides, energy balance manage heat and power to save the cost. And material balance ensures the right amount of raw materials being used. In acetone production, there are two main steps, which is reactive and non-reactive unit operation. The reactive step is where the chemical reaction takes place. It is processed isopropyl alcohol undergoes dehydrogenation to form acetone and hydrogen. After the reaction, the non-reactive step focuses on separating and purifying the products. To obtain pure acetone, processes like distillation and filtration are used to remove unwanted substance.
Fluid mechanics is important in chemical engineering, especially for designing piping system. In acetone production, a good pipeline setup ensures smooth material flow while keeping energy use and cost low. In this project, we will design a piping system by choosing the right pipe size, fittings, and connections. We will also study pressure drops to understand how fluid resistance affects flow. This helps make the system more efficient and reduce energy loss. To move acetone from the processing unit to the storage tank, we will use fluid mechanics principles like pressure drop analysis, flow rate optimizations, and pump selection. We will estimate the pump power needed to keep the system safe, practical, and efficient. A well-designed piping system will improve production, lower costs, and ensure smooth operations.
For the reactive unit operation, the first method is we need to construct the chemical equation. And here is the chemical equation is from the IPA turned into the acetone and hydrogen gas. So the assumption that need to be taken is the first one is the machine is operating 365 days. The production rate is equal to 8.33 kg per hour and has the latent purity. The feed is equal to 149.75 kg per hour. That include is 0.67 and 0.33 isopropyl alcohol and water. The rate of conversion is 92%. And the last one is the endothermic reaction occur. So the extra heat is needed to prevent the heat loss. As for the component of mass and molar flow rate, we use the material balance to get the value from the mole flow rate. After we got all of the value from the mole flow rate and mass flow rate, we can actually get the component of mass and molar fraction. Let's move on to the energy balance for reactive unit. So the first one is the inlet and outlet temperature are 325 Celsius and 350 Celsius. The second one is the inlet and outlet are both in gaseous state with the pressure of 2.5 atm. And the last one, we need to take the reference state as 25 degrees Celsius. So here is the conclusion of the energy balance from the extent of reaction. And here is the final answer that we got for the reactive unit, which is 3.26 kilojoule per second.
Hi guys, so now I'll be presenting on non-reactive unit operations, specifically focusing on separation columns and P calculations related to component mass and molar fractions and energy balance. For example, in our feed stream, acetone has a mass fraction of 0.774 and a molar fraction of 0.381, and the calculation are provided here in the slides. These values will help us understand the composition of the feed entering the separation column. First, let's discuss component mass and molar fractions. These are essential in determining the composition of different components in the stream. To calculate the mass fraction, we divide the component's mass flow rate by the total mass flow rate of the stream. Similarly, for the molar fraction, we divide the component's mole flow rate by the total mole flow rate of the stream. Next, we will talk about the energy balance in a non-reactive unit. In such operations, the total energy entering the system must equal the total energy leaving it, ensuring no accumulation. By applying the first law of thermodynamics, we account for different forms of energy, including heat and work, to ensure accurate process control. An example calculation is provided to illustrate this principle in action. In summary, mass and molar fractions help determine component distribution, while energy balance ensure efficient operation in separation units. Mastering these concepts is crucial for process optimization in chemical engineering.
For the calculation of pressure drop from feed to reactor, we assume the resistance due to enlargement is 1, resistance due to contraction is 0.5. We use 2.5-inch stainless steel pipe with 5 meter long. It is closed system, which pressure feed and pressure reactor is not the same. The velocity is constant because of the same cross-sectional area, no work turbine and work pump. It is steady flow and incompressible fluid, and the fittings is gate valve with 0.13 constant. Next, we find the velocity from the mass flow rate and Reynolds number, which is 21,025.23. It is a turbulent flow because the Reynolds number more than 4,000. Number 3, we find the friction factor and the frictional loss by including all the fittings. In this case, we have 1.163 joule per kg. And then, we substitute the value into the energy equation to find the pressure drop. The pressure drop from feed to reactor is 940.25 Pascal. This is the summary table for pressure drop by including all the fittings with the correct diameter and length.
Now I will explain the delivery strategy for transferring acetone from the feeding tank to the storage tank. This process ensures smooth and controlled fluid movement while maintaining safety and efficiency. So let's take a closer look at the system components. We have an acetone feeding tank which serves as the main product source, a gate valve used to control the flow of acetone, a pump responsible for providing the necessary pressure to move the fluid, a check valve which prevents backflow and ensures one-way movement, and also a storage tank where the acetone is collected and stored. First, efficient pump selection. We use a centrifugal pump with magnetic coupling to prevent leakage and reduce friction losses, ensuring safe acetone handling. Second, optimized piping system. Stainless steel pipes with smooth surface, reduce resistance and pressure drops. Long radius elbows, which is 90° and 45°, minimize turbulence and improve flow. The third one is steady-state flow assumption to ensure a balanced system with no fluid build-up, keeping the process stable and preventing damage. The fourth one is acetone as an incompressible fluid. With a constant density 785 kg per meter cube, acetone simplifies pressure drop and pump power calculations. The sixth one, storage and temperature control. A vertical cylindrical storage tank provides stability. Insulation and cooling keep acetone below 56 degrees Celsius, which is the boiling point for acetone, to prevent evaporation and impurities. The storage tank is made of stainless steel and has a cylindrical shape with a diameter of 6 meters and a height of 4 meters. It has a maximum capacity of 50 meter cube per hour and can hold acetone for up to 9 hours. The tank operates under a pressure of 1 million Pascal and maintains a temperature of 25 degrees Celsius to ensure safe storage conditions. Its design helps maintain stability and efficiency while preventing evaporation and contamination.
For the estimation of pump power, we assume it is closed system where the pressure from the distillation outlet is 130,000 Pascal and the pressure of the storage tank is 1000 kilopascal. It is overpressure to suppress volatility, and the pump efficiency is 78% where the volume of the storage tank is 50,000 liter. Short holding time is used to reduce the risk of evaporations and contamination of the acetone. We find the pressure drop, which is 870,000 Pascal, and substitute the value into the energy balance equation to find the work ideal of the pump. And by using the efficiency, which is 78%, we can find the work actual, which is 1,502 joule per kg, and then times 8 with mass flow rate to find the pump power. And we can also find the holding time, which is 9 hours.
Producing acetone is not just about the chemical reaction, but it also needs good planning to make the process efficient, cost-effective, and safe. There are two main factors, which is principle of chemical engineering and fluid mechanics. For the principle of chemical engineering, there are three main aspects, which is mass, energy, and material balance. Without all of these things, the production can become wasteful and expensive. For the fluid mechanics, it is very important because it helps us to design the piping system that move the materials. There are the things like pipe size, pressure drops, pump power, and storage that must be planned to keep the flow steady and efficient while saving energy and production costs. By using these principles, we can improve acetone production, making it safer, more efficient, and sustainable. This project shows how principles of chemical engineering and fluid mechanics work together to make industrial processes better.
That's all from us. I hope this presentation will help you in order to understand about the principle of chemical engineering and fluid mechanics regarding the integrated design project to produce an acetone. Thank you.